Now we talk about how two resolutions are homotopic. So say consider two modules A and A prime. So these are two R modules, and you're given a homomorphism from A to A prime. So there is a homomorphism here. This homomorphism is F. Now A has a projective resolution, this P0, P1, Pn, Pn plus 1, and A prime has a projective resolution, P0 prime, then you have P1 prime, Pn prime, Pn plus 1 prime, and so on. So you could also consider this as, say, A module having two different resolutions. So instead of F, you could have a ID map here. So in that case, you think of A module having two different resolutions. So here we are saying that A has a resolution in terms of Pi di, and A prime is having a resolution in terms of, we will say, primes, Pi prime and this di prime. Let me just quickly write these di's. So these di's, we will have d0 here, d1 here, dn here, dn plus 1 here. Similarly, you will have d prime n plus 1 here, d prime n here, d prime 1 here, d prime 0 here. So both of these are projective resolutions, so therefore these are exact. Projective resolutions are exact. So projective resolutions are exact. So this we have seen before, and therefore the homology groups here are 0. Now what we want to show is that we are just given this map F. We want to be able to lift this map F to F0 here, lift this F0 to F1 here, lift this F1 to some Fi here, and then Fn here and Fn plus 1 here. So to start with, we are just given projective resolutions of A and A prime. So you're given this, you're given this, and then you're given this map F. So our lemma is that you are able to lift this F to F0, F1, F2, F3, and so on inductively. So this is the first part of the lemma. So let us just prove this part. So let us first construct f of 0, and then we will construct the rest inductively. So for f of 0, we are going to redraw this diagram. So you have this map P of 0 to A. So this is D of 0. I'm just copying this map right here. Then you have A to A prime, which is F. And then you have this P0 prime coming in. So now you can lift this map. So this is, you first apply D0 and then you apply F. So you lift this map, since this P0 is a projective module. After all, we are having a projective resolution. So we can lift this map to this dotted map, and we'll call this dotted map f of 0. So this is our first step. So now we want to say that you have already constructed a bunch of maps. So you have constructed, say, by induction, say you have constructed F0, F1, F2, all the way to Fn. So now we want to lift it to Fn plus 1. So you want to lift to Fn plus 1. So let us see, Fn plus 1 is right here. So let us draw a diagram so that the lifting is possible. For lifting, we are just using the definition of a projective module. So for example, here we said that P0 is a projective module. So you were able to lift this, first apply D0 and then apply F to F0. So let us again write this diagram. Now we have Pn plus 1. And from Pn plus 1, we have this Dn plus 1. You have Dn plus 1. So I will write this here as image of dn plus 1, and then you have this p prime n plus 1, and this gets mapped to image of d prime n plus 1. Now if there is a map here, so we have to show that this map exists. So let me mark this as in red. This we have to show. So if this map exists, then you obviously have a map from here to here, and therefore you can lift this map to our fn plus 1. Yeah, so these maps are natural. This is d prime n plus 1, so you go to image of d prime n plus 1, this is dn plus 1, you go to image of dn plus 1. So if this map exists, so you have a map from image of dn plus 1 to image of d prime n plus 1, then you are able to lift to fn plus 1, because pn plus 1 is a projective module. So this is the only thing we have to show, is this existence here. So if the diagram commutes, that is if this triangle commutes, we can lift to fn plus 1. So we need to show is that f of n acting on image of dn plus 1, so f of n is here, so image of dn plus 1 lies right here. This is where image of dn plus 1 will lie, and this is where image of d prime n plus 1 will lie. So fn, we are saying that fn acting on image of dn plus 1 will take you to d prime n plus 1. So that is, the map here is just f of n, and this map just satisfies the relationship, and therefore we are able to lift to fn plus 1. So we have to just show this. fn acting on image of dn plus 1 lies in image of d prime n plus 1. Now projective resolution is exact, so image is equal to the kernel. So image of d prime n plus 1 is equal to kernel of d prime of n. This is because the projective resolution is exact. So that is, if you say x lies in the image of dn plus 1, then we have to show that then it has to eventually lie, then fn of x has to lie in the kernel of d prime of n. That is, x lies in image of dn plus 1, that is f of x lies in the image of d prime n plus 1, which is equal to kernel of d prime n. So yeah, I mean, instead of x lying in image of dn plus 1, you'll write fn of x, which should lie in now the kernel. So that is, fn of x lying in kernel means d prime n fn of x is 0. So this is what we have to show. So x lies in the image of dn plus 1. So say x lies right here, x lies in the image of dn plus 1. So you applied to some element here, you applied dn plus 1, you get x. Now since this is an exact sequence, you first apply dn to it, dn plus 1 to it, and now you apply dn to it, you get 0. So in pn minus 1 you will get it 0. Yeah, because this is an exact sequence, you have as d square as 0. You compose two corresponding differentials lying next to each other, you will get 0. So you get 0 here. So this 0 will get mapped to 0 right here in p prime n minus 1. And we have to show that the same x, you first apply fn to it and then d prime n to it, you get 0. But that follows from the commutativity of the diagram. This x will get mapped to 0 here in pn minus 1. This 0 will get mapped to 0 here via fn minus 1. And then, since this diagram commutes, you will have x getting mapped to 0 via, you first apply f of n and then you apply d prime of n, and that is what we had to show. So that this x will get mapped to 0 right here. Now we are told about homotopy, that say you are given another gn, that is a homomorphism from pn to pn prime, then these fn and gn are homotopic. So say there is another g0 here, g1 here, gi here, g of n here, then these fn and gn are homotopic. So for that we have defined this map alpha n. So you first apply alpha n and then you apply d prime of n plus 1. So you will have, so we will start with alpha n. So first we will have alpha minus 1 right here. Then you have alpha 0 right here. We have so on. So notice that, so for f0 and g0, for n is 0, you will have alpha 0 d prime n plus 1. So you're going from here, alpha 0 d prime n plus 1, you end up here. And say the second portion, you go from here, you go first d0, and then you have alpha, this subscript minus 1, you end up here. So this is alpha subscript minus 1. So you are anyway going from p0 to p0 prime. So you're saying g0, this f0 minus g0 is nothing but, so this f0 and g0 basically are homotopic. So this was the homotopic condition which we discussed in lecture some time ago. And the reason for this was very clear, because if the maps are homotopic, then we do not have to worry about changes in homology or cohomology groups. And we are given alpha minus 1 as 0. So for f0 minus, so this is the homotopic condition. So we have to show this homotopic condition for, say, starting with 0, because we have to start with induction. So you have f0 minus g0 is equal to, so alpha minus 1 will be 0. So let us just write this down, what this will become. This will become d prime of 1 alpha 0 plus alpha minus 1 d of 0. So alpha minus 1, so d of 0 alpha minus 1, and then you have first apply alpha 0 and then d prime. So this was 0 because alpha minus 1 is 0. So we have to show that f0 minus g0 gets somehow lifted. So let us show this. So we have projective module, so that's the only way to lift the map. So we have to first show this map, image of d1 prime, and then you have p1 prime right here. So we have to be able to show that this map lifts up. So you obviously have this natural map d1 prime, and here we will have f0 minus g0, and then you will show that this f0 minus g of 0 lifts to alpha 0. This is what we have to show. So we have to only show that from p0, if you apply f0 minus g0, you land an image of d1 prime. Now that is kind of trivially true, because so you have f0 minus g of 0, you apply d prime of 0 to it, you get 0, because from p0, if you first apply f0 and then d prime of 0, you land here. Again you apply g of 0 and d prime of 0, you get the same element here, because this diagram is commutative. You know, there is existence of an arrow g0 also. So you subtract this green dot from this green dot, you get 0. So that is what we are saying. Now that means that this f0 minus g0, this lies in the kernel of d0 prime, which is equal to image of d1 prime, because we have an exact sequence. Projective resolutions are exact. So image is equal to the kernel of the map. So so you have that image of f0 minus g0 will lie within image of d1 prime. So you have alpha 0. So now we want to construct alpha n plus 1, given that you have alpha 0, alpha 1, alpha 2 all the way to alpha n. Again we have to construct a projective map. Now in this case you have pn plus 1, and you have p prime n plus 2, d prime n plus 2. Exactly the same way we are going to copy, and you have image of d prime of n plus 2 right here. So we have to be able to copy this map up right here to alpha n plus 1. So in order to construct this map, we first notice this condition for n plus 1. So we have to show this f of n plus 1 minus g of n plus 1. This is equal to d prime of n plus 2 alpha n plus 1 plus alpha n dn plus 1. So basically we will take this side, this thing, and move it on the this side. You get minus alpha n dn plus 1, and that's what we want to show. So this will hold if you show that image of fn plus 1 minus gn plus 1 minus alpha n dn plus 1 lies in the image of d prime of n plus 2. This is what we want to show, and that is precisely what is the map here. So the map here is fn plus 1 minus gn plus 1 minus alpha n dn plus 1. So since you have exact sequence of projective resolution, this image is equal to the kernel. So you have to apply d prime of n plus 1 to this element, and it should give you 0. So you apply d prime of n plus 1 to this, it should give you 0. And our inductive step is fn minus gn is equal to d prime n plus 1 plus alpha n minus 1 dn. So now we have nothing much left to do except actually apply this d prime n plus 1 to this element right here. So let us do this. So you have d prime n plus 1 fn plus 1 minus d prime n plus 1 gn plus 1 minus d prime n plus 1 alpha n dn plus 1. So alpha n is right here. So let us first focus on this one. So you can see that we would want to take this dn plus 1 constant outside. Yeah, we are going to use this inductive step. So we have this element d prime n plus 1. So d prime n plus 1 is already here. So we will take this dn plus 1 common outside. So let us try to bring these other two terms also into times dn plus 1, and then you will take this dn plus 1 outside, and you will get a useful inductive step. So let us focus on this now. fn plus 1, you first apply fn plus 1, and then you apply d prime n plus 1. So fn plus 1 and then d prime n plus 1 is same as you first apply dn plus 1 and then you apply fn. So I'm going to replace this with this new term. You first apply dn plus 1 and then you apply f of n. So what about this one? So you first apply, it says gn plus 1. So gn plus 1 is like here, and then you apply d prime n plus 1. So instead of that gn plus 1 to d prime n plus 1, you first apply dn plus 1 and then you can apply gn. So we are going to replace this again by you first apply dn plus 1 and then you apply gn. So first apply dn plus 1 and then gn. So let us make this substitution right here. So this expression now becomes fn dn plus 1 minus gn dn plus 1 minus d prime n plus 1 alpha n dn plus 1. Take dn plus 1 outside, you get fn minus gn minus d prime n plus 1 alpha n, and then you have dn plus 1 here. Now this entire thing, focus on the inductive step here. So you can have fn minus gn. Now you take this term this side on the left hand side, fn minus gn minus d prime of n plus 1 alpha n will be equal to, this will be alpha n minus 1 dn. So you can rewrite this as alpha n minus 1 dn composed with dn plus 1. Now you have two d's next to each other. This is 0, so you get this equal to 0, and that is what we wanted to show. So that is the end of the story. So again, if you have two projective resolutions of the same module A, so instead of A prime you write A here, instead of F you put ID here, then those two projective resolutions would be homotopic. And that is what we mentioned too in the previous lectures.